Hello, today we're going to talk briefly about momentum and impulse. Momentum is defined as inertia in motion, and if that's not a physics definition for you, I don't know what is. Think back to when we talked about Newton's laws of motion. The law of inertia was an object will remain at rest, remain in a straight line motion unless some outside force acts upon it. Okay? And we talked about inertia as being directly related to an object's mass. So the more mass an object has, the more inertia it has. So our physical quantity that measures inertia is mass. If an object is in motion, what is it definitely doing? Or what does it definitely have, I should say? And of course, it's velocity. Okay? It does not necessarily have to be accelerating, but it definitely has velocity. So when we calculate momentum, we just multiply the object's mass times its velocity. And we use a lowercase p to represent momentum. Capital P, remember, was power. Lowercase p is momentum. It's a vector quantity, so direction matters. If you have the momentum of an object traveling to the right, and we make that positive, and you have an object that's traveling to the left, its momentum must be negative because it's in the opposite direction. There's no derived unit for momentum. So our mass we measure in kilograms, our velocity we measure in meters per second. And so kilograms, meters per second is your unit for momentum. Nothing exciting there. No joules, no newtons, just kilograms, meters per second. Let's take a quick example here. Say a car has 24,000 joules of kinetic energy and has a momentum of 2,100 kilogram meters per second. What are the mass and velocity of the car? So we should be able to recognize at this point that kinetic energy is 1/2 mv squared. And we just said momentum was mass times velocity. So they have the same variables. So what we can do is we can make a substitution here and determine what these values are. Kinetic energy, no, 24,000 joules is 1/2 mv squared. Momentum, we just said was 2,100 kilograms meters per second. And that equals mv. Okay? What does 1/2 mv squared really mean? Or think about back to your days when you first learned algebra. You know that this is really 1/2 mv times v. So where we have the mv, we can substitute in our 2,100 kilogram meters per second. Okay? If you wanted to, you could solve for m in terms of v and the number, or solve for v in terms of m and the number, however you want to do it. This is the easiest way for me, but you can choose to substitute however you want to. Okay, so where we have the mv, we can now put 2,100. So 24,000 joules equals 1/2, and I'll write this in blue to show our substitution, times 2,100 kilograms meters per second times v. 1/2 times 2,100 is 1,050. So we say 24,000 divided by 1050. And we get that the velocity of our car is 22.86 meters per second. And we can then take that and plug that back into our relationship over here. And we can determine that the mass is the 2,100 divided by 22.86. And we get the mass of our car is 91.88 kilograms. So obviously not a real full-size car. Maybe it's some kind of little Tonka truck or a motorized car for a small child. Okay? So that's how you would do that problem. Setting up, making substitutions, having the same variables into two different equations. Impulse is defined as the change in an object's momentum. So if we set this up, the letter we use to represent impulse is the letter J. Okay? And the reason we use J is because I is used for current, which we'll talk about later in the semester. But J is our unit we use for impulse, and that equals delta P. Okay? So change in momentum. We know the delta means, of course, final minus initial. So it could be final momentum minus initial momentum. Most of the time when you have an object's momentum changing, it's going to be its velocity that changes. So we can instead plug in mass times change in velocity. Okay? Think about that. When a car changes its momentum, it's usually speeding up or slowing down. It's not like the bumpers falling off, or you have something jumping on top of the car, those kind of things. So it's the change in the velocity. From this equation right here, we can come up with a different expression. All right? Remember when we saw delta V a long time ago? And over here on the side, remember that A, acceleration, equals delta V over t. Okay, V final minus V initial over the time. So if we then multiply both sides times t, we can solve for delta V. And we get that delta V equals A times t. So now we can substitute that in for our delta V. So now we can write the impulse, J, equals M times AT. And hopefully you see something, instead of just spelling mat, which of course you can see that, hopefully you also recognize the fact that we have an MA. And we should remember that MA equals force. So another expression we have for impulse, it's equal to a force times the time. Okay? And just like we talked about with work, this force is for an average or constant force. Okay, no variable forces. We don't know that yet. That involves a little integration in our calculus. We'll get to that when we take AP. But looking at this, impulse, the change in object's momentum, equals the force applied to an object times the time over which the force is applied. This is very important for lots of different things in your everyday life. Okay? The role of time. All right? If we say that J equals F times T. Okay? Let's say we have two different eggs. We have one egg that's going to fall down onto a flat surface. It's going to fall straight down. What's going to happen to the egg? Of course, it's going to splatter everywhere. Okay? What if instead we have an egg that's going to fall down to some nice lush grass? Okay? Maybe you're outside having an Easter egg hunt. Maybe you're just playing with eggs outside for whatever reason. If it lands on the nice lush grass, what's going to happen to the egg? Okay? Hopefully it doesn't break. Hopefully we just have a nice solid egg sitting in the grass. All right? If you look at the two examples here, if they both drop from the same height, the speed at which they hit the ground is going to be the same. Okay? So they're going to have the same final velocity at both places. Okay? The velocities are the same, the masses are the same. If they then stop, they come to a rest after they hit the ground, we know that the change in the momentum will be the same. Okay? But what's different when you hit the nice hard sidewalk versus hitting the nice soft grass? Okay? And the answer is this time. Okay? If the impulse is the same, and t increases, we should be able to recognize that force will decrease. Okay? Think about jumping into a ball pit or a nice, like a sponge pit, jumping on your bed versus jumping on the floor. In a car crash, the use of an airbag versus hitting the steering wheel or the dashboard. Those are all examples of the time being increased, which then decreases the force that your body experiences. Okay? So a very important idea there. When we have an object's change in momentum being the same, all things being equal, except for the time changing, the time of stopping usually is what you look at, the force will decrease. Alright? So real quick there, a little momentum and impulse for you. Thanks!